Okay, Assalamualaikum, a very good day. So we're going to proceed with the next topic, still with the image enhancement topic. So we are going to look for the topics on the derivative, on the gradient, and the sharpening process. Okay, so we go back to the to this particular map, right? So for the previous one, we already talk about the processing, and then we have the spatial filtering with this a smoothing filter. So far we already covered the filtering process, which using the kernels that like the box and average, all those stuff. So we are going to work on today about this one. So it is under sharpening filter. So we are going to look at the derivative one here, right? So this is the one. Okay, and then we are going to look at the order of the gradient here. Let me just point options. Okay, so we're going to look at the first order here, and the next one will be later on, which is the next topic, right? Okay, let's go back to the basics one on the filtering, on the spatial filtering. Where the filters we are going to do the smoothing last week. So for the smoothing, right, basically the process is a process of integration, you call it. So this is the integral process, so where you are doing the plus and do all the averaging based on the pixels. Whereas for the sharpening process, we are going to talk about derivation process, which is the dy/dx process. So this is basically back to your maths basics in your secondary school. So we are going to look at the process. We are not going to look at the mathematical version. Just directly go for the profiling on the derivations. Okay, before we proceed, we go back for the concept of the regions. So you can imagine back, right, from the image where, for example, we have the grayscale here. So this is a grayscale image. Alright, so if you can zoom down, last time we are using the IM tools to get all the image grayscale values. So this is a part of it. So you can see here, this is likely all the values are nearly the same. So the type is actually very constant. So the intensity is very constant. So there is no changes, no big changes over here. So the first one, they call it the constant intensity regions. So let's look at the second one. They call it the intensity ramp, just a ramp only, just a ramp. You can see here. Here you can see this is actually the brighter place here. Then you have the darker place here. So the changes between this part and this part is actually not that big. Alright, so they just call it an intensity ramp. Whereas the last one here, on the third area over here, they call it the intensity step, which is very sharp edges. Step means from very dark to very high. So you can see here there's a very dark, and later there is a background that is quite bright. So you can see, if you zoom down, so you can see that the grayscale value is actually very dark and going jump to very bright. So this is quite very sharp edges, they call it. Right, so these are the normal regions that you can find in the image, especially on the grayscale. Alright, so what is the gradient? So if you play with the words of Microsoft, there are actually numbers of gradient that you can play around. But here, which is very simple, what does it mean is this image gradient is a directional change in the intensity or color in an image. So the intensity, you are talking about the grayscale. Here is the grayscale image, whereas the color is the one, the RGB, all those things, right? So grayscale here, you are looking at the gradient directional change. So you can see the directional here. This is the direction. Alright. Okay, the changes in intensity. So the changes here, you can see from here, then the intensity change here. So this is going to be your edge over here, right? So it is a measure of change in image function fxy in x direction rows and y direction columns. So this is your x and this is your y. You will calculate one by one. So normally, right, gradient is used to detect the edge. For example, you can run the Sobel operator to find the edge of this guy. So this is the edge of it. This is for example. Alright, so let's look at the next one. Go back to the basic concept of a gradient by using the digital edge. So this is the ideal case where you can see here, for example, this is let's say just go from 0 to 255. So this is very steep, right? So model and ideal, this is very ideal digital image. So gray level profile of horizontal line through the image, you can see here, for example, this is dark and this is going to be white. This is not really white, so maybe around 150, you just get one. So this is, if you go for white directly, means that it's 255. So this is between 0 to 150. So the steep changes here is between this one. This is the changes from dark to the bright area. This is the ideal case. It's very step, just a step one, right? 1, 0 and 150. But the thing is, in the model of RAM digital image, right, this is not really there. I mean, this is the one that normally we can get the slope. So it will have the profiling from start here, then you have the RAM here, right, go up, and then you can have the brighter version. So this is the RAM area. This is not like this one, very steep, and it has a step. Alright, so this is because of the optics or some things on image. This is related to the lower we have. Right? Okay, now we have to go back to the mathematics versions on the profiling. Alright, so this is actually just now the digital image gradient profiling. Alright, so what I did tell you just now is the derivation process is the one that we're going to learn here in the sharpening process. So integration is related to the smoothing. So sharpening is related to derivation. Okay, let's look at the profiling here. So the derivation is related to dy dx for the 2D, which is we are going to have the fxy, right? This is the one, right? So let's look at the first derivative here. This is your grade level for just now. This is the profile just now. So if you do the derivative, right? I'm not going to do the mathematics at the moment, so we just look at the profile. So if you have the first derivative for this particular image, right, you look at the positive. Okay, here the RAM, we always go for a point here going up, right? So this is the, when you have the RAM, you have the first derivative is high. Okay, without any RAM, this area, okay, so there will be zeros, there will be 0 here, right? Here there will also be 0 here. If there is a changes from here to here, right, then you have this particular spike over here. So this is the profile of the derivation on the first order. Okay, this is call it the first derivative. So what does it mean? That positive at the points of transition into and out of the RAM. So it means that it's going up, transition here, then it's going to have a positive value here, right? And then after finish the changes here, it will go back down here because there is no more changes or RAM here, right? So this is what the meaning for the second one. So constant for points in the RAM. So it means that there is a points here. This will be a constant here, right? For points in the RAM. This is positive, is this one, right? Okay. So later the last one, 0 in areas of constant gradient. So this is will be the 0 areas. This is going to be the 0 areas. So this is a positive RAM. So this is actually a RAM. Going down is also positive RAM. Okay, so this is the first derivative, right? So the conclusion is, what does it mean? That the first derivative says for this particular two different intensity variable, right? So the magnitude of the first derivative can be used to detect presence of an edge. So this is going to be the magnitude you're going to calculate, and based on the magnitude you can find an edge. Where is the changes between these two? There is a gradient, then you can find an edge. So they are going to look at the first derivative. The second derivative is on the other lecture, is related to the sharpening kernel. So we are going to look at the first derivative first. Alright. So first derivative in image processing are implemented using the magnitude of the gradient. So we are going to find the magnitude of the gradient, okay, based on this one. So it is significant local changes of intensity. Intensity, this is for example the grayscale of value in an image, and typically occur on the boundary between two different regions in an image. It's the same one like this one just now I show you guys, where you have a bright version over here and then you have the darker version over here. So between the changes here, the process can detect an edge by using the first order derivative process for the gradient. Okay, this is example again. If I zoom down for an image, a pixel of 6 by 6, right? So if you look at the intensity wise, so here this is quite dark, and then let it jump to 90. This is also like that, the same example here. So in between this one, we can see the ramp, the changes of the intensity, right? So we know that basically this might be an edge after we do the processing. So same goes to this one. You can see the edge over here. This one still can see the edge because there are changes on the light and dark side. So same goes to this one. So you can see here, this is later. If you do any threshold, then you can find the you can find the edge of the image. All right. So what are the operators? What are the kernels, or what are the masks? What are the the filter that we use for the gradient? All right. So there are two types over here. Actually, there are more than that, but we are going to cover two. Mostly one, basically. So the first one, they call it cross gradient. This is actually a 2x2 kernel, and the other one, they call it a Sobel operator. All right, this is 3x3, and there are two of them, both of them, because they are looking at the two axes, y and x. Because if you look at the what you call that one just now, this is the one. The image function affects in x direction and y direction. So we have to do 2 times to get the final magnitude. Right? There are two direction, x and y. Okay, let's look at the first one. This is just briefing on the Robert cross gradient. So this is actually a very first edge detector for the 2D image processing. You can get this one, and this is basically using the concept cross diagonal differences. You can see here and here, the rest is at 0, the rest at 0. Same goes to this one, changes here. And if you mix up this kernel, this is -1 plus 1 is equivalent to 0. Same goes to this one. So this is going to work on the diagonal only. So it means that if you have an image like this, 6 by 6, 3 by 3, right, it only can cover up to this one only. So there's the issues on that, basically. Based on that one, the 2 times 2 kernel are not easy to implement, and number of calculations are more, and calculations only with diagonal and not neighborhood pixels. So only calculate based on this one. So even though this is a smaller kernel, but normally it tends to give more errors, more noise, because you are not calculating most of like the neighborhood process like this one. We learn about the convolution, so we are not considering the rest of the neighborhood pixels, the connectivity, or the adjacency. All right, so it's going to be not really what you call that. The noise may interfere, may get more on that, right? Okay, let's just directly go to the Sobel operator. Okay, so we go back to this one. This is going to be a Sobel operator. This is the kernel, kernel or the mask, or the filter, we call it. So you are looking at this one. The value here, same, the sum all here will be going to be 0, same with this one. So this is for the x direction, this is for the y direction. Okay, let's look at this one, how it works. So sorry, so this is x, sorry, and this is y. Okay, the Sobel operator performs a 2D spatial gradient measurement on an image and that corresponds to edges. So again, this is a spatial gradient measurement. To measure the gradient, it's a 2D spatial where we're still learning about the spatial for the image enhancement. So it is used to find the approximate absolute gradient magnitude at each point in an input grayscale image. So if you have an image, you run this one, you can find the absolute gradient magnitude. Okay, and the third one, we have to understand that the operator consists of a pair of 3x3 convolution. Okay, kernels are shown in below. But the thing is, because it's already divided into two areas, gx and gy, okay, one kernel is simply the other rotated by 90 degrees. Previously, we learned about convolution is 180 degrees. We need to flip the x and y. Then you can do the process of the neighborhood process, the processing. So for the case of Sobel operator, we had divided to gx and gy. So it means that one time here 90 degree, another one here is 90 degree. So for the case of this one, right, for this one, when you want to do for the gx one, so the flip will be here flip 90 degrees. So there will be no flip on the other side here. So again, if you flip this one, go to here, it will be the same. And also if you flip here, go to this one, it's going to be the same. You're not going to flip to the other one, to the other side. Alright, so if you flip, then this is going to be a different number. So because of only 90 degree for the particular gx, you're going to flip this 90 degree only. So same goes to gy. Gy, when you want to flip, right, you're going to look at the flipping here. This is a 90 degree flipping, and this is going to be the same one. So it's not going to be flipped this one like this one. So see, there will be only 90 degrees. So if you do this one, right, it's going to have the same kernel, same mask, same filter value. So it means that you can do the direct convolution from the kernel that we have over here. Right, it's the same thing. So when you want to do the gx one, right, so you're going to look at the results here. For example, you can find out later the intensity may be like this, and for the y direction you can do get like this. So this is the output result. So later you have to combine all these things and you get one result to get the final one. Okay, let's look at the Sobel again. Okay, the theory again, this one. So if you look at here, right, so this is a x direction here, right? If there is any changes, right, for this direction, so this is x direction, x, so you are going to have the changes derivative here. So there is no changes on 0, which is from no changes in y. So y, if you going down, there is no changes in the gradient. It's the same value. Okay, so you're going to have only for this one. And then for the particular this one, if you look at this particular example here, so for the y, if you go this direction, there is no changes also, and no changes also. Right, so if you go to this direction, then you see there is the changes from here to here. This is dark, this is lighter. So this is by degree angle. You can see here, like this is more darker, and then you are going to go for the other side. This is lighter. So both x and y got difference on the gradient. Alright, so the formula to get the gradient magnitude used is given by g square plus gy square, gx square plus gy square, and you can get the square root, you can get g, and then the gradient's direction is by having the arctan from gygx. Then you can get the values. Alright, so this is going to be the calculations more on the matrix now. Okay, what does it mean? What is gradient magnitude? Okay, gradient magnitude is the measurement, right? How strong the change in image intensity. So based on this one, right, you can see the changes here. Okay, this is quite dark, right? So let's say, for example, the changes here, how big the changes is based on this one. So you can see here 12 to 90, 12 to 8 to 12 to 8, 88, 12 to 84. So this is even higher magnitude. This is lower magnitude. So this is the measurement on how the change in image intensity, they call it. Alright, so the next one, the directions of the gradient, which is this arctan. This is the directions where is the image is changing most rapidly. Alright, so this is the calculation you need to understand with these two. Alright, let's look at the example here, Sobel operator. Okay, we have an image here. You can see here this is 100 all the while, and then the next one is 50. So this is a darker version. So this is a lighter version here. So there is a gradient here. Here you can see a jump, a ramp from here to here, here to here. So we can say that this is actually a gradient from this one to the other side, right? So this is like x direction here. Okay, so let's try to calculate one of them, right? One of them here, pixel here. You do convolution with the x kernel, and then you get the y here to get the gy here, and then this is gx, right? You calculate based on the convolution because this is already flip. If you flip also, it's the same. You flip here, it's also the same. There's no changes. So you just do the calculations here, all this one, and then finally you can get the value here is equivalent to plus 200 for gx. Okay, next one. If you calculate for the gy area, right, gy direction, and then you can calculate later, you have it will be 0. Alright, so you get this value, right, to 200 square plus 0 square. Finally you can get the value is 200. Right, for here to go here, there's changes here. The intensity, not the intensity, the intensity is 150. The measurement of the gradient is around 200. Alright, so the directions of the gradient is 0 degree. Is it 0? So this is 0 degree. This is going to this direction, so this is 0 degree because this is x and this is y. So it's correct. The direction here is from here and go to here. So this is directions, which is 0 degree. Okay, this is how you calculate the gradient by using Sobel operator. Okay, so this is the example again, but I want you guys to calculate again and to find what will be the value for G, the gradient measurement, and the directions of it. So this is going to be the remove here, 20. I'm going to remove for this one. So this is not correct. You have to find the value for gy and gx for doing this one, and also you need to calculate again on this one. Then you find the g value and also the directions of the gradient. So you have to put this one all in your quiz answers. I'm going to put the questions and the option of answers inside the quiz. Alright, so this is just to add up. If you have all the Sobel operator done, right? So if you are doing any threshold process, finally you can get the age. For example, like this one, this is going to be RGB colors. You do the process of Sobel operator. You find the age. This is combination of GX and GY. Then you get this one, and you can make another process, another execution where you want to find the threshold. If more than 100, you're going to make it black, or other than that it's going to be zero. Like for example here, all zero, right, means it's going to be white. So this is actually how you have to do the threshold process. This is the one that we learned before. So the thing here we just need to understand is the Sobel operator can be used to detect an edge. Basically, it is based on the gradient calculations. Okay, so this is the one that you need to complete. We're going to look at the other lectures on the sharpening. So thank you very much for this one.